Great, so this is the exercise we are going to solve. As we can see, it is an open traverse. There's a small gap between A and K. Okay, so in this question, we have two benchmarks or two control points, point A and point K. And here we have the coordinates and the azimuths of the two benchmarks given in the question. So the question says find the adjusted coordinates of points B, C, D, and E shown here. And we are going to start this question. So here we have 6 steps which we have to follow to solve this question. We'll go through the steps one by one, starting from step 1 and going to the last step where it shows compute the coordinates, and this is the final result which we require. So let's get started with the step 1, compute the azimuths of all lines. By going back to the question first, we can see that there are two azimuths given to us, azimuth of line AB and azimuth of line EK, and we are required to find the azimuths of the three lines BC, CD, and DE. To find out the unknown azimuths, I prepared this page. Going back to the question first, we can see that azimuth of AB and azimuth of EK are given, and I wrote them here in my page in black color. So now I'll start with azimuth BC. As we can see, azimuth BC is equal to back azimuth of AB plus clockwise angle, and we discussed those things in part 1 and part 2 of the video. So azimuth of AB, when we need the back azimuth, if it is more than 180, we have to deduct 180. Okay, so 186 degrees 15 minutes and 0 seconds, it's more than 180, so we'll say minus 180 degrees, okay, plus the clockwise angle. Okay, let's see how to find out where is the clockwise angle. Let's assume that we are driving through line AB and going to line BC. So going from line AB to line BC, we have two angles. The first angle is from line AB to BC, this angle, and the second line we have is this angle. We can understand that this one is the clockwise angle and the other one is the counter clockwise angle. Okay, so we need the clockwise angle and the given angle is the counterclockwise, so we can say that 360 minus the given angle, we can get our clockwise angle. So 360 degrees minus 215 degrees, 53 minutes and 0 second. So azimuth of BC is equal to, let's do the calculation, 186 degrees 15 minutes 0 second minus 180 degrees plus 360 degrees minus 215 degrees, 53 minutes and 0 second. So we'll get here 150 degrees, 22 minutes and 0 second. This is the azimuth of BC. Now going back to the previous page, we have found one of the three unknown angles. So we can consider this sheet as our summary sheet. So let's note the angle of BC in this page here. great. Okay, now let's go to azimuth of CD. Azimuth of CD is equal to back azimuth of BC. So azimuth of BC is 150 degrees 22 minutes and 0 second. It is smaller than 180 degrees, so we'll add here 180 degrees instead of subtracting, plus the clockwise angle. Okay, again, now regarding the clockwise angle, let's look at this sheet. Going from BC to CD, we have two angles. We have the red one, which is counterclockwise, and the other way we have the clockwise angle, which is the one we require. So we need to get this clockwise angle, and again we'll say 360 degrees minus the counterclockwise. So 360 degrees minus 51 degrees, 40 minutes and 0 second. Azimuth of CD is equal to, let's make the calculation, 150 degrees 22 minutes 0 second plus 180 degrees plus 360 minus 51 degrees 40 minutes and 0 second. So we'll get our result 638 degrees 42 minutes and 0 second. Because this value is more than 360 degrees and our angle should be between 0 and 360 degrees, so we'll deduct 360 degrees from our angle. 638 degrees 42 minutes and 0 second minus 360 degrees. This will be our azimuth, 278 degrees 42 minutes and 0 second, and this will be our azimuth of CD. So now let's get back to the summary sheet and note the second azimuth. Here's our summary sheet. Let's zoom in. This is our CD, so I'll just note it here, and we got our second unknown azimuth. Let's zoom out again. Okay, so we got two angles, we need the third one and the fourth one just to make sure. We are done with azimuth CD. Now we'll proceed to azimuth of DE. Azimuth DE is equal to back azimuth of CD plus clockwise angle. So back azimuth, we have the azimuth of CD is 278 degrees 42 minutes and 0 second, which is more than 180 degrees, so we have to deduct 180 degrees plus the clockwise angle 360 degrees minus our angle 111 degrees 6 minutes and 0 second. So let's do the calculations. This time you can find the clockwise angle by yourself. 278 degrees 42 minutes and 0 second minus 180 degrees plus 360 minus 111 degrees 6 minutes and 0 second. Okay, so our result will be azimuth of DE is 347 degrees 36 minutes and 0 second. So we are done with our unknowns now, but we have to do this last step just to make sure that everything is going right. Let's note this azimuth in our summary sheet. This is our summary sheet. Let's zoom in here and Note our angle 347 degrees, 36 minutes and 0 second. Okay, we'll zoom out again. We can see that we have found 3 unknown angles. Now this last step is just to make sure we have the angle of EK. It was given in the question, it's written here in black color. So we want to make sure that the result we'll get here, it is exactly similar to the given azimuth in the question. So azimuth of EK is equal to back azimuth of DE, which is 347 degrees, 36 minutes and 0 seconds. It's more than 180, so we'll deduct 180 degrees plus the clockwise angle 360 degrees minus 124 degrees, 36 minutes. Okay, and the azimuth of EK is equal to, let's do the calculations, 347 degrees, 36 minutes and 0 second minus 180 degrees plus 360 degrees minus 124 degrees, 36 minutes and 48 seconds. So we'll get our result here 402 degrees, which is more than 360. So here we have to deduct 360 because our angle must be between 0 and 360, minus 360. Again, we'll do the calculations. 402 degrees, 59 minutes and 12 seconds minus 360. Oh, so here we'll get 42 degrees, 59 minutes and 12 seconds. Okay, so now comparing this result we got here with the azimuth given in the question written in black, let's pull it down here. So comparing those results, we can see that those values are not equal, which means that we have some errors. Those errors are called misclosure errors. If they were similar, we would skip step 2, but there is some misclosure error, so we have to proceed now to step number 2, where we'll find this error and we will remove it. Let's get started with step 2, find the angular misclosure and do the corrections. First of all, we have to find the angular misclosure, which is equal to the calculated azimuth of EK minus the measured or the benchmark given azimuth of EK. So from the previous page as shown, we can find that the calculated is 42 degrees, 59 minutes and 12 seconds minus the measured 42 degrees, 59 minutes and 0 seconds. So this will give us an angular misclosure of positive 0 degrees, 0 minutes and 12 seconds. So in our open traverse, we have a small misclosure error of 12 seconds. We need to get rid of this error. It's a positive error, so we need to deduct it from each angle until we get 0 misclosure error. Okay, so now to distribute this angle on the angles, or distribute this misclosure on the angles, we have to know what is the correction per angle. So the correction per angle is the angular misclosure, which is 0 degrees, 0 minutes, 12 seconds, divided by number of calculated angles, as shown in the last page. So number of calculated angles, we have calculated 4 angles in the last step. So we have to divide the misclosure by 4 and we'll get 0 degrees, 0 minutes and 3 seconds. But this time we have to keep it negative because our total error is positive 12 seconds. So we need to deduct 3 seconds from each angle so we can reach 0. Okay, now let's get started with the correction. So when we go to the correction, look at the way I'm going to distribute the error. The first line AB is a benchmark, so there is no correction in the first one. Okay, in the second line BC, I am going to deduct negative the error 3 seconds into 1, which is equal to 3 seconds. For line CD, this time I'm going to deduct 3 seconds but times 2, which is equal to 6 seconds. In the third line, I'm going to deduct 3 seconds multiplied by 3, which is going to give me 9 seconds. And in the last one, EK, I have to deduct 3 seconds into 4, which will give me 12 seconds. So I can mark the corrections. Okay, why we did it in this way? Because the error is cumulative. Okay, so let's look at this page to understand why is it cumulative. Okay, so first of all, we have to know that this point A marked in red, this is a benchmark. A benchmark is the only thing which we are referring to. That's why we didn't add any correction to line AB, because we considered line AB to be a benchmark, and the azimuth taken at AB, which is from A to B, is a given azimuth with a given value, so it is correct and no need to make any corrections on it. Now, we made the first setup, we kept this total station equipment here to get the azimuth of this line. When we distributed our misclosure error, we noticed that each measurement or each azimuth has to take 3 seconds of error. This device or this equipment had an error of 3 seconds. This was the error of this equipment which affected line BC. Okay, when we go to the next line, which is, or the next setup, which is setup C, this setup was used to get line CD. Okay, so this setup was used to get line CD. And now the error of this equipment is 3 seconds as well. But now, because I took the mistake from the previous setup, okay, so 3 seconds, the mistake of this device, and then I will add 3 seconds for this device, we'll get here 6 seconds. Similarly, we'll move to the next setup, and we need to know the error of this line. So we have the error of this equipment is 3 seconds, here 3 seconds, here 3 seconds, we'll get 9 seconds. So let's return to our question, and now we understood why those corrections are cumulative. Now we can go and step forward to find the corrected values. So in the first one, there was no correction, so I'll get the same angle, which is 186, 15 seconds and 15 minutes and 0 seconds.
Okay, in the second one, we have to deduct 3 seconds from this azimuth, and we'll get 50 degrees, 21 minutes and 57 seconds. Here we have to deduct 6 seconds and we'll get 278 degrees, 41 minutes and 54 seconds. Here we have 347 degrees, 35 minutes and 51 seconds. And here we have to deduct 12 seconds, we'll get 42 degrees, 59 minutes and 12 seconds. So these are the corrections. And sorry, my mistake, 0 seconds, so we deducted the 12 seconds.
So now when we return to the main question, we can see that this number here is equal to the benchmark given in the question. So now our azimuths are correct. We can proceed to the next step and compute the departures and the latitudes. Let's start with step 3. Compute the departures and the latitudes. Before we start with this step, we have to first understand why do we need those departures and latitudes. Because those departures and latitudes are the ones which will get the coordinates. The concept is very simple. Okay, let's have an example.
For example, I'm having a line, let's say AB, and along with this line I have an angle of 45 degrees, let's assume. Okay, the length of this line is 100 meters. Okay. In this question, I have the coordinates of point A, which is 0x and 0y. I need the coordinates of the question mark and question mark on the y-axis. This is the exact similar question to what we are solving at the moment. So normally in mathematics, or whatever subjects we study those things, in surveying, geomatics, mathematics, physics, how do we solve this question? Simply, we draw a horizontal line, and we call this line delta x. Then we plot a vertical line, and we call it delta y. These are the departures and the latitudes. So this is the departure versus the latitude. So how do we get this departure? Delta x is equal to 100 cosine 45, and delta y is equal to 100 sine 45. Then when we go to the new coordinates, our new coordinates are going to be in the x, it will be 0, the one from here, plus 100 cosine 45 will get us the x, and for the y, 0 plus 100 sine 45.
Simply, this is going to be the procedure we are going to follow. Now let's go and find the equation using the length and the azimuth. We need to make an equation for the departure and the latitude. So now for all the lines, we will be using the length and the azimuth. So we need to find a formula so it will be easier to calculate. Anyways, let's assume this is line AB, and we have the north arrow, here's the azimuth and the length. So to find the departure, this line represents the departure or the delta x, and this line represents the latitude or the delta y. Now to get this delta x, we can say that this is length sine azimuth, and we are going to find the y. We can say that this is length cosine azimuth.
Okay, so these are the two formulas I'm going to use for all the cases. So departure is L sine azimuth, and latitude is L cosine azimuth.
Okay, so now let's proceed to the main table, which we are going to make all our calculations in it. This is the table we are going to use. We have the first column, which is the A, B, C, D, E, and if we can notice, those values are written between A and B. Okay, because this length is for line AB, but when we go to the coordinate, the last two columns, it is exactly in front of A, because this is the coordinate of point A, but those are the data given for line AB. First of all, we got the lengths from the question as shown here, and the azimuths, these are the adjusted azimuths. We got them from step 2 of this question as shown as well. Now I'm going to calculate the departure and latitude of all lines using the formulas we got from the previous page. So we got that the departure is L sine azimuth, and we got our latitude as L cosine azimuth. We got all the lengths, all the azimuths, so it will be easy to calculate those values. So let's start with the departures one by one. The length 1895.3, sine azimuth 186 degrees 15 minutes and 0 seconds. So here we'll get a negative 206.335. Next we have 1751.8, sine 150 degrees 21 minutes and 57 seconds. We'll get 866.196.
Next we have 1977.8, sine 278 degrees 41 minutes 54 seconds. Here we'll get a negative 1955.052. Next 1423.9, sine 347 degrees 35 minutes and 51 seconds. We'll get a negative 305.822. Finally we are with 2341.8, sine 42 degrees 59 seconds 59 minutes and 0 seconds. We have 1596.605.
These are the departures. Now we'll go and find the latitudes. Instead of sine, we'll just replace it with a cosine. So we have 1895.3 cosine 186 degrees 15 minutes and 0 seconds. We'll get a negative 1884.035. Next 1751.8 cosine 150 degrees 21 minutes 57 seconds.
Again we get negative 1522.665. Next 1977.8 cosine 278 degrees 41 minutes and 54 seconds. We'll get a positive 299.107. Next 1423.9 cosine 347 degrees 35 minutes and 51 seconds. We'll get a positive 1390.670. Then 2341.8 cosine 42 degrees 59 minutes and 0 seconds. We'll get a positive 1713.149.
We are done with the departures and the latitudes. Now we can move forward and find out what are the coordinates. So let's start with the x coordinates, then we'll proceed to y. What we have to do exactly is we will get the first coordinate, which is the 6000. We'll just add the departures one by one and note the coordinates, the x coordinates or the easting coordinates. So when we say 6000 minus 206.335, we'll get the coordinate x coordinate of point B 5793.665. We'll add 866.196. We can get the x coordinate of point C as 6659.861.
Again, we'll add the departure here. We'll get 4704.809. Again, we'll add this value and we'll get 4398.987. And finally, we'll add this value here to get our final coordinate of x coordinate of point K to be 5995.592.
We are done with the x-axis. Now I'll use the blue color to find out the y-axis coordinates of the points. The same procedure will go in blue color. So 5000 minus 1884.035, we'll get here, oh sorry, this is the black color, 3115.965 minus 1522.665 to get the y coordinate of point C. We'll get 15.
3.3. Again, we'll add this value. Get 1892.407. We'll add this value again. And we get 3283.077. We'll add 1713.149 finally, and we'll get here 4996.22.
6. These are the coordinates of all the points B, C, D, E, and K. As we did in step 1, if you remember the last part where we calculated the azimuth of EK, we compared the azimuth with the azimuth given in the question to make sure if we have some misclosure errors or angular misclosures or not. The same thing we'll do it now, so we can make sure if we have some linear misclosures or we don't. So when we go back to the question, we can see that the given coordinates of point K are in the x-axis 599.7.3, which is does not equal this number here, and for the y-axis we have 4997.1, which not equal this number as well. So here we have to go to step 4. Step 4, compute the linear misclosure and the relative precision. When we zoom in here at point K to see how it looks, actually there is a small gap. How did I know there's a small gap? From the photo shown here, there are some differences in the x and y, the calculated ones, and the benchmark given in the question. So when we go here, we can see that this line here, this is the linear misclosure we are looking for. But how can we get this linear misclosure? At the moment we have the total error in the x-axis, and we have the total error in the y-axis. Okay, so let's calculate those. Departure error is equal to 599.5.592 minus 599.7.3. Here we'll get a negative 1.708, and latitude error is 4996.226 minus 4997.1. We'll get a negative 0.874. So when we get back to the zoomed part, we can see that this small part in the x-axis is equivalent to 1.708, and the part in the y-axis is equivalent to 0.874. To find the linear misclosure, which is the red line here, we'll use Pythagoras theorem. Linear misclosure is the square root of the departure error squared plus the latitude error squared as well. So let's calculate this linear misclosure. We have our departure error from the previous page. We got negative 1.708 squared plus our latitude error negative 0.874 squared. We'll get the linear misclosure as 1.918 meters. Moving forward to the relative precision, we can calculate the relative precision, which is the linear misclosure 1.918 meters over the total length of the traverse. We will add the lengths so we can get the total length of the traverse. We have 1895.3 plus 1751.8 plus 1977.8 plus 1423.9 plus 2341.8. The total length of our traverse will be 9390.6 meters. We'll get 1 over 4896, which is approximately, let's say, 1 over 5,000, which means in every 5,000 meters we have a 1 meter error. So in the next step we are going to get rid of the linear misclosure. Step 5. Adjust the departures and the latitudes. Adjusting the departures and the latitudes is directly related to the length of the lines. Longer lines will have more correction than the shorter ones. So the information we'll need here is the length of each line. For AB, this is the departure for AB, so the length of line AB would be 1895.3. For line BC, it will be 1751.8. CD 1977.8. DE 1423.9, and finally EK 2341.8. Similarly, we'll be having the same lengths for the lines in the latitude. I'll just copy those values here. Nine 7.8, 1423.9, and 2341.8. So as we said, it is the correction is directly related to the ratio of the lengths comparing with the total length. So we will divide the length of each line by the total length of the traverse. The total length of the traverse, as shown in the last page, it was 9390.6. So this will be same for all of the lines on both sides. 90.6, 9390.6. 0.6. It's just like taking percentage of line AB here. It's just like taking percentage of line AB related to the total length of the traverse. Okay, now because our error was negative when we calculated the error in the shown page, it was negative, so that's why we are adding to remove those, to get rid of those errors. If it was positive, we'll keep here negative. So we'll multiply this ratio by the error of departure, which is 1.708. Similarly, this ratio of this line multiplied by the same error of departure, 1.708 and 1.708. For the latitude, it was negative as well, so that's why we kept plus sign here. We will multiply by the latitude error, which was 0.874. Okay, now we are done with our correction. We'll just do the calculations. So now let me note the correct departures. For the first one, we'll be getting negative 205.990. Here we'll be getting 866.515.
Negative 1954.692. Negative 305.263. 1597.031. You can do the calculations by yourselves. Now I'll be doing noting the corrections of the latitude values. Here we'll be having a negative 1883.859. Negative 1522.502. 299.291. 1390.803 and 1713.367.
Those are the adjusted departures and the latitudes. Now we can proceed to the last step and compute the coordinates. Step 6. Compute the coordinates. This will be the final result of our work and the final step. We will do the same procedure we have done in step 3, compute the departures and the latitudes. The same thing we'll do here. We'll start first with the x coordinates of all the points. So here we'll say 6,000 meters minus 205.99. We'll get 5,794.01 plus 866.515. We'll get 6,660.525. Again, minus 1,954.692. We'll get 4,705.833 minus 305.563. We'll get 4,400.270, and finally we'll add 1,597.031 and we'll get 5,997.3. And this is the coordinate which was given in the question as a benchmark, so our work is perfect here. Let's move to the y-axis. So we'll say 5,000 meters minus 1,883.859. We'll get 3,116.141 minus 1,522.502. We will get 1,593.639 plus 299.291. We'll get 1,892.93 plus 1,390.803. We'll get 3,283.733 again plus 1,713.367. We will get 4,997.1, and this is also the exact value which was given as a benchmark in our question. So we are done with this question. These are the coordinates required, and that's all.